Hey guys, my name is IBM and today I've decided to take you to papers. These are paper 4-1. This is October-November 2024. This is paper for A-level structured questions. But before I take you to the paper, I would like to remind you of our website www.caieresourcemaster.com, where we shall be keeping our resources, past papers, even these solved papers will be saved there with their answers written on. So you can always visit. The site is just growing, so you may not find all the resources you need, but I'm very sure that most of the physics resources are there. Unfortunately, most of the physics resources, apart from the past papers, may not be free, so they are for purchase. And if you wish to purchase, I would just like to show you how our site looks like. So our site looks like this. You can select your level, maybe A-level physics. And under A-level physics, you'll find tutorials, topical questions, past papers. There will be predicted papers by examiners. I don't know when, but there could be predicted papers in the future, especially whenever we are a few months or like 1-2 months to the exams. There will be predicted papers in this folder. So in case you want to let's say obtain topical questions, of course these I don't think they are free. Topical questions may not be free. They're only free to my students, I think, because I'm the one who uploaded them. I'm the one who designed them. So my students may get them for free. For you may not get them for free. So in case you want set purchase topical questions, you can obtain them here. So here I only see paper 4 topical questions. These are past paper questions which have been solved in the videos, especially in my videos. And if you try to click to purchase this, when you try to complete the download or the purchase, to look like this. After completing the purchase using PayPal, it will look like this, and you just click download and download your document for any purpose, for any use. So do not forget, you can create a free account and always access our resources for free, especially the past papers. Of course, the past papers here, you find them here for free. You can download the past papers of the previous about 4 to 5 years. You can find them on our website. Here are the past papers. You can find them here. The question papers and their mark schemes. You can always find them there and download for your revision purposes. Okay, so just to take you back to what we were doing, solving October-November 2024, paper 4, A-level structured questions. I'll just go through a few of the constants. I think most of the constants you are familiar with them. However, we'll just talk about one of the formula which is very important, which is this one here. This one here. This formula is very important because when I relate it to PV equals to nRT, and I compare this with the PV equals to, when I make PV the subject here, it is a third, N M mean square speed. When I combine these two equations, you will notice that, by the way, remember PV equals nRT is the same as NKT. This can be the same as NKT because we know that R equals to N over, sorry, it's not R, it's N, number of moles. Small letter n, number of moles is equal to N over Avogadro's number. And when you combine those two equations, you have that PV equals to, where there is number of moles, you put N over Na times R, then times T. And R over Na is KT. That's why I said PV is also equal to NKT. And from your nuclear physics, from your ideal gas parts, therefore you have that PV is equal to NKT, and PV is equal to a third Nm mean square speed. So PV equals to NKT, and PV equals to a third n m mean square speed. So n cancels out. Of course, when you combine those two equations, when you equate this to this, n cancels out, which means 1 over 3 m mean square speed is equal to kt. So you may need to have this knowledge. For example, you multiply both sides by 3 and multiply both sides by a half. You'll have a half m mean square speed equals to 3 over 2 times kt. And of course, this is kinetic energy of a molecule. So you have an idea that the kinetic energy of a molecule is 3 over 2 times kt. Okay, I just wanted to show you how to use that formula for different purposes in this paper. The rest of the equations will be used directly, I think. Let's start with the question number 1. State Newton's law of gravitation. Of course, we know the gravitational law. So we shall say that the gravitational force between two point masses. You should be referring to point masses. This law only applies to 2 point masses. Is directly proportional to the product of the masses and inversely proportional to the square of their separation. Okay, so I'm trying to be very slow because I want to make sure that my handwriting is readable. Some students said I need to improve their handwriting. So the gravitational force between 2 point masses is directly proportional to the product of the masses and inversely proportional to the square of their separation. Those are very important parts for this statement. A planet may be considered a uniform sphere. A satellite is in a circular orbit of period capital T around the planet at a height h above the surface of the planet. The height of the orbit can be adjusted by using a satellite's rocket engine. The figure 1.1 shows the variation with h of t power 2 over 3. So the planet is a sphere, so I will draw a sphere. Let's say that is the planet. And the satellite is in a circular orbit at a height h above the surface. So let's say the satellite is somewhere here. And this height is h above the surface of the planet. So it means the distance from the center of the planet. This is the planet. The distance from the center of the planet, let's say it's radius. I'll just use small letter r. Okay, let me just use small letter r to be the radius of the planet, or rp to be the radius of the planet. So the radius of orbit of the satellite is going to be rp plus h. Okay, so the figure shows h plus the variation of h of t squared, t power 2 over 3. By reference to the forces, explain why the orbit of the satellite is circular. Of course, first of all, we know that the gravitational force between the two masses is the one which provides the centripetal force. And the reason as to why the gravitational force provides the centripetal force is because it always acts perpendicular to the direction of motion of the satellite. And because it acts perpendicular to the direction of motion of the satellite, it doesn't change the speed, but instead it changes the direction, causing the body to move in a circular path. Therefore, I would simply say that the gravitational force acts perpendicular to the direction of motion of the satellite, and thus just provides the centripetal acceleration. Let me just use centripetal acceleration. Thus just provides a centripetal acceleration. So the acceleration of a body moving in a circle is the centripetal acceleration. I would have said just provides centripetal force. It's the same thing after all. Centripetal force is directly proportional to the centripetal acceleration. Okay. Use Newton's law of gravitation to show that h and t are related by h plus b cubed equals to ga over 4 pi squared, then t squared, where g is the gravitational constant, a and b are constants that depend on the properties of the planet. Okay, so we are going to use Newton's gravitational law. We have already seen that the gravitational force provides the centripetal force. So the gravitational force provides centripetal force. Okay, so we know that the gravitational force is going to be capital G. The mass of the satellite, I'll call it capital M. I mean the mass of the planet, capital M, and the mass of the satellite, I'll use small m for the mass of the small satellite. So small m. Then let their separation be x. So I would say x squared. That is the gravitational force. You know this equation from your concepts of gravitation. This should be equal, because to provide centripetal force, so this should be equal to m, the mass of the satellite, times v squared divided by x. But of course, we know that this small m cancels out first. And of course, we know that v equals to omega times x, or omega r if you were using r. That is v is equal to omega x. And of course, we also know that omega is 2 pi over t. So I'll first simplify this. I have this as g m equals to, where there is v squared, I'm going to put omega squared times x squared, then divided by, of course, one x cancelled here. Okay, I'll just say omega squared x squared divided by x, then I'm cross multiplying, then times x squared. So in other words, capital G, capital M is going to be equal to omega squared times x cubed. Okay, and we also know that omega is equal to 2 pi divided by the period. Now that is squared, we have that G capital M equals to, when I square 2 pi over t, it becomes 4 pi squared over t squared. Then this should be multiplied by x cubed. Okay, so I'm going to try to rearrange this to look like what has been given in the question. So trying to rearrange this equation, I'm going to make x cubed the subject. So x cubed is going to be equal to g m then divide by 4 pi squared times t squared. So in comparing the two equations, when I compare, comparing gives x cubed is the same as h plus b cubed. So x cubed is going to be h plus b cubed. And this means, because h was the height of the planet, and remember x is the radius of orbit, x cubed is equal to h plus b, which is the radius of orbit. And remember, the radius of orbit is measured from the center. Hence, it means b equals to the radius of the planet. The radius of orbit, remember I said if this is the planet and the satellite is at this height h, x is the radius of orbit, which is measured from the center. So it means b must be this radius of the planet. So if that is h and that is x, b must be this radius of the planet. Hence b equals to the radius of the planet. That's number one. Number two, when we compare again, we notice that m is going to be equal to a. So m equals to a, which is the mass of the planet. Hence, I would just say h plus b cubed equals to capital G A over 4 pi squared times t squared as required. Then use the gradient and intercept of the line in the figure to determine values of a and b. So looking at this equation here and the graph which has been plotted, let's see the graph. The graph is t power 2 over 3 divided by, against h. So I will try to manipulate this equation to make t over 3 the subject. So we have that h plus b cubed equals to capital G A, which is the mass, divided by 4 pi squared t squared. So I find the cube root first. I'll have that h plus b equals to G A over 4 pi squared. This is to the power of 1 over 3 times t squared to the power of 1 over 3, which becomes 2 over 3. That is finding the cube root, both sides. And then because it is against h, I have again to make, I must make t squared, t power 2 over 3 the subject. So t power 2 over 3 is going to be equal to h divided by the cube root of this, so divide by G A over 4 pi squared power 1 over 3 plus b divided by the same thing, that is G A over 4 pi squared power 1 over 3. Okay, so when I compare this with the, when I just simplify this further just a little, 2 over 3 equals to 1 over g a over 4 pi squared. This is power 1 over 3 times h. Then plus b divided by g a over 4 pi squared power 1 over 3. So it means comparing this with y equals to mx plus c, you notice that the gradient, let me change the color here to highlight this. So you notice that because we have plotted t squared on the y-axis has been plotted, h on the x-axis has been plotted, so the gradient is going to be that. So it means the gradient equals to gradient equals to 1 over capital G A over 4 pi squared power 1 over 3. I think that is the gradient. I think mathematically this is the same as 4 pi squared divided by G, because it is 1 over that, so it is 4 pi squared divided by GA raised to the power of 1 over 3. Okay. So if I get the gradient, I'll equate to that. So I'll just go to the graph and try to see if I can find the gradient. So I'll take this point here. I think that is according to the scale, 400 divided by 10. Each of this is 40. So this is going to be 360. Then this one, this is going to 12 to be 12. I think it's 1280. Then on the x-axis I have 0 and 12. So that is the gradient. So the gradient is going to be 1280 minus 360 divided by 12 minus 0. So that is just 12. But remember it was 10 to the power of, I think, 6. Should be equal to 4 pi squared over GA. And remember, G is the gravitational constant, which is known as 6.67 times 10 to the power of minus, I think it's minus 11. And A was the mass of the planet, which we are trying to find. So we have only one unknown here. So this is going to be equal to G, which is 6.67 times 10 to the power of minus 11, then times A, sorry, it is 4 pi. So this is going to be 4 pi squared divided by 6.67 times 10 to the power of minus 11, then times A, and this is raised to the power of 1 over 3. So I'm just going to raise the gradient to power 3, then I cross multiply and find the answer. So A is going to be equal to 1280 minus 360 divided by 12 times 10 to the power of 6. No, it is 4 pi first. I'm trying to make A the subject. Whichever way you use to make it the subject, I'm just raising this to the power of 3, raising the gradient to the power of 3, and then making A the subject. So A is going to be equal to 4 pi squared divided by divided by 1280 minus 360 divided by 12 times 10 to the power of 6, but this is raised to the power of 3, then times 6.67 times 10 to the power of minus 11. What I did was just multiplying, raising this to the power of 3, and raising this to the power of 3. I mean multiplying this side by 3, the other side by the power of 3, and this side by the power of 3. So that this 3 cancels this one, and again I make A the subject. So I did this all because I wanted to just press my calculator once. So I'll press my calculator now. So starting from the denominator, I'll find 1280 minus 360 divided by 12 exponent 6, then times 6.67 exponent minus 11. Then I will say 4 pi squared divided by the answer. So I'm getting A as 7.7. Did I press this correctly? Let me try to repeat it again. 1280. I think I didn't raise this to power 3. 1280 minus 360 divided by 12 exponent 6. Answer raised to power 3. Okay, yes. Then times 6.67 exponent minus 11. Then I will say 4 pi squared divided by the answer. That's 1.31 times 10 to the power of 24. So A is 1.31 times 10 to the power of 24. So 1.31 times 10 to the power of 24. The unit, of course, is kilograms. Of course, I had to doubt a mass which has a power of 15 for a planet. It was really not interesting. Then B, when you look at this graph here, you notice that B, if you look at this expression here, you notice that the y-intercept is equal to B times 1 over GA over 4 pi squared raised to the power of 1 over 3. In other words, the y-intercept equals to B times the gradient, because 1 over GA over 4 pi squared times 1 over 3 is the gradient. So it is B times the gradient. What does that mean? It means B is going to be equal to the y-intercept divided by the gradient. So from the graph, I will just look for the y-intercept. I think the y-intercept was 360. So I'll just say this is equal to 360. And the gradient was 1280 minus 360 divided by 12 times 10 to the power of 6. This was the gradient. So from my calculator, I have 1280 minus 360 divided by 12 exponent 6. Then I'll say 360 divided by the answer. So it's 4.695 or 4.7 times 10 to the power of, these are 6. So this is 4.7 times 10 to the power of 6. Now what are the units? The y-intercept was t squared over 3, which is seconds power 2 over 3 divided by The gradient was s power 2 over 3 divided by h. Let me see here. I'm trying to find the units for the gradient. We have s power 2 over 3 divided by m. That was the units for the gradient. So here we have y-intercept divided by the gradient. So s power 2 over 3 divided by s power 2 over 3 over m. So s power 2 over 3 cancels out and the m goes up. So this becomes just m. So the unit here is going to be m. So this is going to be 4.7 times 10 to the power 6 and the unit is meters. That is 5 marks. I've spent a lot of time on that because I wanted to explain a lot. Define specific heat capacity. Specific, that is 1 kilogram, and heat capacity, that amount of heat required to change the temperature by 1 Kelvin. So I'll say the thermal energy required to change the temperature of 1 kilogram of a substance by 1 Kelvin. Thermal energy required to change the temperature of 1 kilogram of a substance by 1 Kelvin, or you can quote thermal energy per unit mass required to change the temperature by 1 Kelvin. Thermal energy per unit mass, because specific, that is 1 kilogram, we consider unit mass. So the thermal energy per unit mass required to change the temperature by 1 Kelvin. So Kelvin is capital K. So two solid blocks X and Y are made from different metals. The blocks have different initial temperatures. Block Y is initial at room temperature. The blocks are placed in direct thermal contact with each other at a time t equals to 0. The figure shows the variation with the T of the temperatures of the two blocks. Okay, so we see that they are reaching the same temperature, so they are reaching thermal equilibrium. But this is starting with 25. Initial temperature is 25 degrees Celsius. That is why X is initial temperature is, let's see, the scale is 25 divided by 10, 0.25. So 1, 2, 3, 4. So what is that? So that is 4 times times 2.5. So it is 85. This is 85. The initial temperature of the other one is 85. Okay, so they reach the same temperature. What is this equilibrium temperature? So the final temperature is this one, I think. No, it's not that one. Is it this one? I feel like final temperature is this one. Final temperature is this box here. So that is 1, 2, 3, 4, 5, 6. So you have 6 times 2.5, 15. 15 plus 25, 40. So the final temperature is 40 degrees. State 3 are conclusions that may be drawn from the figure. The conclusions may be qualitative or quantitative. Of course, I've tried to give some of the conclusions here. Do I have enough space? Okay, I'll try to write some of the conclusions here. Number one, we have seen that final temperature for both is 40 degrees. So final temperature of both equals 40 degrees. We have seen that the initial temperature of X was 85 degrees Celsius, and we have also seen that the initial temperature of Y is 25 degrees Celsius. Or we can look at the temperature changes. Of course, this has changed from 40 to 25 to 40, so it is 15. The other one has changed from 85 to 40. So temperature change for X temperature change of X is going to be 85 minus 40, which is 45 degrees Celsius. Temperature change of Y is going to be 40 minus 25, which is 15 degrees Celsius. Then when you look at 45 and 15, you could say temperature change for X is 3 times temperature change for Y. So I could also say temperature change temperature change of X is 3 times temperature change of Y, because 45 is 3 times 15. So you could also add they have reached thermal equilibrium. The blocks X and Y reach thermal equilibrium. That's why they reach the same final temperature. You could also talk about the heat capacities of each of these. Let me see. We know that Q equals to mc delta theta, which means that mc equals to Q over delta theta. And m times c is actually the heat capacity. So heat capacity of, if we look at X, its heat capacity, they're made from different metals. They have different initial temperatures. So if heat capacity is Q over delta theta, you notice that Q Q over delta theta is going to be bigger for Y and smaller for X because heat capacity is going to be Q over delta theta. If the same amount of heat is supplied, the change in temperature is bigger for X than for Y. And when delta theta is bigger, then heat capacity is smaller. So the heat capacity for X is less than that for Y. Then, of course, we can make an assumption that there is no heat loss to the surrounding. Otherwise, if there was some heat loss to the surrounding, the graph would be showing that. So I can also add that the blocks end up in a thermal equilibrium at 40 degrees Celsius, as we have seen. Then I can also say heat capacity, that is the amount of heat required to raise the temperature of the whole substance. So heat capacity, not specific, but heat capacity. Heat capacity of Y is larger or is bigger than heat capacity of X. Then, of course, I talked about the graph does not indicate any thermal loss to the surrounding. So we can say heat loss to the surrounding is negligible, or we can say there is no heat loss to the surrounding. So this is 1, 2, 3. You can come back and add any of these 4, 5, 6, 7, 8, and so on and so forth. The ratio mass of block Y over mass of block X is equal to 1.3. The metal in block Y has specific heat capacity of 901 joules per kilogram per Kelvin. Determine the specific capacity of metal in block X. So we are going to consider, of course, for specific capacity, that is the amount of heat required to raise the temperature of 1 kilogram of that substance. Okay, so we know that Q equals to mc delta theta, which means and remember, by the way, m times c is the heat capacity. So m times c is going to be equal to q divided by delta theta. And delta theta for x, we saw I think it was 45 degrees Celsius. The change in temperature for y was 15 degrees Celsius. So I'm going to have the mass of x, okay, the mass of y, specific capacity for y, is going to be equal to q times delta theta for y. Similarly, the mass for x, specific capacity for x, is going to be q divided by delta theta for x. Now I'm going to divide these two equations because I want m of y over m of x. So m of y, cy, over m of x, cx is going to be, here now I get the reciprocal, I'll cancel out q. So this is going to be delta theta for x divided by delta theta for y. Remember, m of y over m of x is 1.3. So I'll say 1.3 times specific capacity for y over specific capacity for x equals to change in temperature for x is 45. Change in temperature for y is 15. So 1.3 times 901 divided by C for x is equal to 3. So C for x is going to be 1.3 times 901 divided by 3, which is equal to 1.3 times 901 divided by 3. So that is 390 approximately. So the answer here is going to be 390. State what is meant by Avogadro's constant. Of course, we know that Avogadro's constant is the number of particles or atoms in 0.01 kilograms of carbon-12. The number of particles, call it atoms, in 0.012 kilograms of carbon-12. That is Avogadro's number. Or you can define it as the number of particles per unit amount of substance. Number of particles per unit amount of substance. Number of particles per unit amount of substance, because we know that number of moles is equal to the number of particles divided by Avogadro's number, which means Avogadro's number is equal to the number of particles divided by the number of moles, and the number of moles is the amount of a substance. So I can define Avogadro's number as the number of particles per unit amount of substance. State the relationship between Avogadro's constant Na and the molar gas constant R and the Boltzmann's constant K. Of course, this is where I started it from. We said that PV was equal to nRT, and we say this was capital N over Na times R times T. And we say that R over Na was equal to a new constant that we called K. So K is equal to R over Na. Or you can write it the other way around, that Na equals to R over Boltzmann's constant K. Two samples X and Y of ideal gases are both thermodynamic at thermodynamic temperature T. Sample X has volume V and consists of N molecules and the mass M. Sample Y has volume twice V, consists of 2N molecules and mass 2M. Complete the table by giving expressions in terms of sum or all of N, M, T, V, and the constants in A Roman 2 for the quantities indicated. Constants, that is K, R, and Na. Okay. So for X, we want to first find the pressure. So we said PV equals to nRT, where we have said this is the same as number of molecules of Avogadro's number times R times T, where we say this is the same as NKT, because R over Na is K. So we have that PV equals to NKT. So for X, its volume is V. Its volume is V. I'm just making P the subject. So pressure of X is going to be the number of molecules was N, then times K is a constant. They were all at the same temperature T divided by the volume V. So for X, it is going to be N kT divided by V. Then for Y, pressure of Y is going to be N, number of molecules was twice N, then times K times temperature was initially the same. The volume for Y is twice V. So this is divided by 2V. So this cancels. So it is still going to be the same, NKT divided by V. So the pressure here is also NKT divided by V. Then amount of substance, that is number of moles. Amount of substance, that's number of moles. So we know that number of moles equals the number of molecules over Avogadro's number. The number of moles for X is going to be the number of molecules, which is N, over Avogadro's number, which is Na. So this one is direct. So it's N over Na. The number of moles for Y is going to be the number of molecules, which is twice N, over Avogadro's number, which is Na. So this is going to be twice N over Na. Okay, we're done with the number of molecules. Then let's check the mean square speed of molecules. The mean square speed of molecules. So earlier on I showed that, I think I showed earlier on that if we combine PV, equals to say NKT, I've already derived that, and the equation which is given in the list of formula, PV equals to 1 over 3 mn mean square speed. When we combined these two and equated them, we had that a third mn mean square speed was equal to nkt, and n cancelled out, and we saw that the mean square speed, making mean square speed the subject, is going to be 3 kt divided by m. Okay, now let's look at the x. For x, the mean square speed is going to be 3 kt over the mass of x, which is m. Then for y, the mean square speed for y is going to be 3 kt over the mass for y, which is 2m. So I'll just write here 3 kt divided by m and 3 kt divided by 2m. Then the last one is internal energy. Of course, internal energy is the sum of the total kinetic energy of all the molecules. So from this equation here, we notice that kinetic energy, or you have that m mean square speed equals 3 kt, multiply both sides by a half. So you have that a half m mean square speed is equal to 3 kt over 2. That means that kinetic energy of a molecule is going to be 3 over 2 kt. That's kinetic energy of a molecule. Then total kinetic energy of the gas. So total kinetic energy of the gas is equal to the internal energy, which is going to be equal to kinetic energy of a molecule times the number of molecules. So that is going to be 3 over 2 kt times the number of molecules. So for x, it's going to be 3 over 2 kt times n. And for y, it's going to be 3 over 2 kt times 2n. So for x, internal energy is going to be 3n kt divided by 2. Then for y, the 2 cancels out it will be 3n kT. As simple as that. Okay. The temperature of sample X is now varied. On the figure, sketch the variation with the thermodynamic temperature of the root mean square speed of the molecules of the gas. Okay. So we have already seen that the mean square speed is equal to 3 kT divided by m. So if they say we are looking at the temperature of the sample X is now varied. Of course, 3 is constant, K is constant, the mass of the gas is constant, so it means the mean square speed is directly proportional to T, which means that the root mean square speed is going to be directly proportional to the square root of T. We find the square root. So it means when T equals to 0, the root mean square speed is also going to be 0. Our graph starts from here. We can just check the shape by using simple substitutions, but if you're a mathematician, a graph of a quantity directly proportional to the square root of the other one is going to be one which has a decreasing gradient. In other words, to be a curve with a decreasing gradient. However, if you can notice, it means that C increases more rapidly than T. Because C is squared and T was not. If I find a square root, still it means the root mean square speed. I mean, in that case, it's going to mean that as C increases, C increases as the square root of T. So in other words, T increases more rapidly than the root mean square speed. So it is going to be a curve with a decreasing gradient. Alternatively, we can check when T equals to 1, let's say root mean square speed equals to a constant times 1. When T equals to 2, root mean square speed equals to a constant times the root of 2. When T equals to 3, then the root mean square speed equals to a constant times the root of 3. So you notice that at all times, T is increasing more rapidly than the root mean square, because the root mean square is the square directly proportional to the square root of T. So that means there's going to be a graph of a decreasing gradient. State what is meant by simple harmonic motion. Of course, we know that for simple harmonic motion, acceleration is equal to negative omega squared times x. So acceleration is directly proportional to displacement, and acceleration and displacement are always in opposite directions. So this is going to be periodic motion in which acceleration is directly proportional to displacement and acceleration is always in opposite direction to displacement. Acceleration is always in opposite direction to displacement, or you can say acceleration is always directed towards the fixed point, or A is always directed towards a fixed point. The fixed point is the equilibrium position. A block is suspended from a spring as shown in the figure. The block is pulled down and released at time t equals to 0. So it means it's pulled down, therefore h decreases, because h is the distance between the bottom of the block to the ground. So it means at t equals to 0, h is a smaller value. It is then, this is at t equals to 0, h is small. It then oscillates vertically with simple harmonic motion. The figure shows the variation of the velocity v of the block with height h of the base of the block. Of course, if at t equals to 0, the block is at the lowest point, so h is small. That means the velocity is 0 at t equals to 0. And therefore, here, that is a very important point for the displacement and this one here. Okay. Determine the amplitude in centimeters. So we're going to find the amplitude by just considering these two positions. So this one and this one. And I will divide this by 2. I think this is 3. That is 3 point something. 3 point. This is 3, 1, 2.5, 3.5. So here we have 3.5, and here we have 9.2.4.5. That is 9.5. So the amplitude is going to be 9.5 minus 3.5 divided by 2. So the amplitude is going to be, which is also x naught, is 9.5 minus 3.5 divided by 2. The diameter of that circle divided by 2. So that is 0, 6. So that is 3.0. Show that the angular frequency is 3.2. So we know that our maximum velocity is equal to omega times maximum amplitude. And we know that V naught from the graph, V naught maximum velocity is, I think this is the maximum velocity. I think that is 9.5 because the scale here is 0.5. So that's 9.5. So maximum velocity from the graph is 9.5 centimeters per second. So it means omega is going to be V naught divided by x naught. So that is going to be 9.5 centimeters per second divided by x naught, which is in centimeters. So omega naught is going to be, that's 3.0. So 3.0, 9.5 divided by 3.0. 9.5 divided by 3.0. 3.16 recurring. So 3.1667, which is approximately 3.2 radians per second. Because centimeters cancels, it means the units are going to be radians per second. Calculate the period t of the oscillations. Of course, we know that period can be got from omega equals 2 pi divided by period, or the period is equal to 2 pi divided by omega, which is going to be equal to 2 pi divided by 3.2. So 2 pi divided by 3.2, that's 1.96, which is approximately 2.0. So that is 2.0 seconds. On the figure, sketch the variation of h with the time t from t equals to 0 to t equals to 6. Okay. So h is, remember, the height above the base. At t equals to 0, h is 3.5, and the body is at its maximum displacement downwards, which means at t equals to 0, h is 3.5, but it is below the equilibrium position. And the equilibrium position is going to be around 6 point, what is this? Let's say 3.5 plus the amplitude, which is 3, that is 6.5. So the equilibrium position is going to be around 6.5. At t equals to 0, h is 3.5. Then at t equals to a quarter a cycle, that's when it is passing equilibrium, h is going to be at t equals to a quarter of a period, h must be 6.5, that is equilibrium position. It is passing equilibrium. Then at t equals to 3/4 of a cycle, where the velocity becomes maximum on the other side, then this means h must have reached the highest point, which is 9.5, which we saw here. Then at t equals to 1 complete cycle again, h, of course, when velocity becomes 0, the displacement is maximum. H is going to be 9.5. Then at t equals to 1 full cycle, we just come back to where we started from. Okay, so that is now easy to sketch. I'm going to look for 6.5 as the equilibrium position. That's when we have not yet started stretching, because from this graph, 6.5 is the center. 1, 2, 6.5 here is the center. So there, when the height above the base is 6.5, the body is at its equilibrium position. So I'm going to draw to look for 6.5 here. Let me check. 6.5 minus 5 divided by the scale, which is 0.25. So I'll add 6 squares here. 1, 2, 3, 4, 5, 6. So this is 6.5. This is going to be the equilibrium height. So the equilibrium height is 6.5. Not equilibrium displacement, but the equilibrium height is 6.5 centimeters. Then at t equals to 0, it is at the lowest point. H was 3.5 centimeters. So we look for 3.5 from the equilibrium height. We just look for 3.5. So this is 2.5. This is 3, I think. Let me just choose a calculator. 3.5 minus 2.5 divided by the scale, which is 0.25. So I'm going to add 4 boxes. 1, 2, 3, 4 here. So my graph starts from here. Then at a quarter of a cycle, because the period was 2, a quarter cycle, the body goes to equilibrium, which will be here. At half a cycle, the body goes to maximum displacement, whether this is 3.5. Maximum displacement is 9.5. 9.5, let me see how many squares I subtract from 10. I think those are 2. 9.5 could be here. So our graph will not go beyond this. And it will not go beyond this. So at half a cycle, it goes to maximum displacement. 3/4, it comes back to origin. Then full cycle, it goes to the bottom. Then cycle repeats, it goes to equilibrium, it goes to the maximum, it comes back to equilibrium, it goes to the bottom, it comes back to equilibrium, it goes to the maximum, it comes back to equilibrium, then to the bottom. Okay, so I'll draw a smooth curve. Okay, so I think that is the graph. That is the graph. We just use the idea of where is velocity supposed to be maximum. When velocity is maximum, the displacement is zero. So that means the equilibrium position or the displacement is zero when the height is 6.5. That's where the velocity is zero. State the relationship between electric field and electric potential. We know that electric field is equal to the negative potential gradient. So electric field is going to be equal to the negative potential gradient. It's the negative potential gradient. Two charged isolated insulating spheres X and Y are near to each other as shown in the figure. P is a point on the line joining the centers of the spheres. Explain why it is not possible for the total electric potential and the resultant electric field to simultaneously be zero. They can't be zero at the same time. The reasons are very simple. Number one, if the potential is to be zero, one charge must be positive, another one must be negative. And yet, if the electric field strength is to be zero, both charges must be either positive or both charges must be negative. And charges cannot be both positive and again negative and positive at the same time, you know. So number one, we can say for potential to be zero, for potential to be zero, the charges must have opposite signs. Must have opposite signs so that one potential is positive, so that one potential is positive, so that one potential is positive and the other is negative, so that they cancel out. And the other potential is negative 2 to cancel out. That's number one. Number two, they said explain why. So for potential to be zero, the charges must have opposite signs so that one potential is positive and the other potential is negative to cancel out. Then how about electric field? So I'll say that but for the field to be zero, for the field to be zero, The charges must have the same sign. The charges must have the same sign so that the fields due to x and y are in opposite directions to cancel out. So that the fields due to x and y are in opposite directions to cancel out. And of course, it's just common sense that charges cannot be positive, both positive, and again one positive and negative at the same time. It's practically not possible. So since the signs of charges cannot simultaneously be both the same and again opposite, then it is not possible. Since the signs of charges cannot simultaneously cannot be simultaneously cannot simultaneously be both the same sign and again opposite and again opposite, then it is not possible. So it's not possible. The magnitudes of the charges on sphere X and Y in the figure 5.1 and Q and 2Q respectively. The spheres may be considered as point charges. If they can be considered as point charges, then the equations for electric potential, electric field strength, and so on can apply. The point P is a distance x from the center of sphere X. The electric potential at point P is 0. Show that the distance y of point P from the center of sphere Y is equal to 2x. So coming back here, we say this distance is x. Electric potential here is 0. So one of these charges must be negative. Let's say this is positive. Let me make this one to be negative. I will make this one to be positive. That's the only condition when we can have v as 0 here. So if this is x, let the other one be y. The distance is x here, and the other distance is y. So using the equation for electric potential, potential is equal to q divided by 4 pi epsilon naught times the distance x. So potential due to x is going to be positive q over 4 pi epsilon naught x, and potential due to charge y is going to be negative twice q divided by 4 pi epsilon naught, the distance I'm going to call it y. This one was called x. So this is y. So remember the sum of these two must be 0 at that point P. So potential at P equals to 0, but is equal to the potential of x plus potential of y. So it means when I add q or positive q over 4 pi epsilon naught times x plus negative 2q over 4 pi epsilon naught times y. I should be able to get 0. And when we solve this, you notice that q over 4 pi epsilon naught x is equal to twice q over 4 pi epsilon naught times y. So q cancels, 4 pi cancels, and epsilon. So we have that 1 over x equals to 2 divided by y, which implies that y equals twice x as required. State an expression in terms of q, x, and the permittivity of free space epsilon naught for the electric field strength Ex at a point P due to sphere X. Of course, we know that electric field strength is equal to Q divided by 4 pi epsilon naught. Now this will be x squared, so that is very simple. So Q over 4 pi epsilon naught x squared. Determine an expression in terms of Q, X, and epsilon naught for the resultant electric field strength E at point P due to the two spheres. Resultant electric field strength. Okay, so because I've already said one is positive, one is negative, it means the electric field strength is towards or in the same direction. So E of field is in the same direction. Because our potential was 0 at P, then the electric field strength cannot be 0. So the electric field is in the same direction. So we are just going to add up. So we have that E for X is this one here. Electric field strength due to Y is going to be equal to twice Q divided by 4 pi epsilon naught times x squared. Times y squared. Where there is y, I'm going to just put there twice x. So times y squared, which is going to be 2q over 4 pi epsilon naught 2x squared, which becomes a quarter, the 4. So this one cancels 2, so it becomes 4, that is 1 over 8. So it is q divided by 8 pi epsilon naught times x squared. So I'm going to find a total. So total E is going to be equal to EX plus EY. I'm just adding because they're in the same direction since we have unlike charges. For unlike charges, the electric field is always pointing towards the negative charge. We have already established that one of the charges must be negative since the potential was said to be 0 at point P. Potential can only be 0 if one charge is positive and another one is negative. And if one charge is positive and another one is negative, then the electric field strength always points in the same direction. So we just sum it up. So this is going to be equal to Q divided by 4 pi epsilon naught times x squared plus, this is going to be, the 2 has cancelled, so that is Q over 8 pi epsilon naught x squared. So mathematical, I think this is going to be common factor is Q over 4 pi epsilon naught x squared into 1 plus 1 over 2. And I think 1 plus 1 over 2 is 3 over 2, I think. So this is Q over 4 pi epsilon naught x squared into 3 over 2. So when you multiply, it becomes 3q over 8. So this is 3q over 8 pi epsilon naught times x squared. So that is 3q over 8 pi epsilon naught x squared. State what is meant by rectification. Of course, rectification, that is converting alternating current, alternating voltage into direct voltage. Converting alternating voltage to direct voltage, or converting AC to DC. State the difference between half wave rectification and full wave rectification. Of course, we know that for half wave, voltage is just a voltage is voltage in one direction is removed, because if this was a full cycle, I want to demonstrate this here. If this was a full cycle, 1.5 cycles, for half wave it would be, for half wave we shall have only that. That means voltage in one direction has been removed. The voltage in the negative direction has been removed. If it is full wave, we shall have something like this, which means for full wave, voltage in one direction is just reversed. Instead of it being removed, it is reversed. So for half wave, so we have voltage in one direction is removed. It is removed completely. For full wave, voltage in one direction is simply reversed. Is So notice the difference. The other one, a half a cycle has been removed, and this one, instead of removing it, it has been reversed. It is reversed. Okay. Complete the figure 6.1 to show a circuit that produces half-wave rectification of an alternating input voltage V in to produce output V out across the resistor R. So to have half-wave rectification, we need a diode. So I will join this part here. I don't need it. Because it's half-wave rectification, I'm only going to draw one diode. So I'll draw this diode here. Okay, so that is half-wave rectification. State the purpose of a capacitor C in the circuit. Of course, the role of a capacitor in a circuit where we have rectification is to produce smoothing. So this is for smoothing. In other words, to prevent or to reduce fluctuations in the unidirectional output voltage. That is what we call smoothing. Reduce variations in the unidirectional output voltage, that is smoothing. The input voltage V in the figure 6.1 is a square wave. The figure 6.2 shows the variation of V in with time t. So here the maximum voltage is 12 volts. So the maximum was 12 volts, which started fluctuating up to 80 volts. The maximum energy stored in the capacitor is 0.041 joules. Show that the capacitance of C is 570 microfarads. Okay. Of course, we know that energy stored by a capacitor is equal to half CV squared. which means that C is going to be twice the energy stored divided by V squared. When I try to substitute, it will be 2. The energy stored is 0.041. Then V was 12. V is 12 squared. So from the calculator, 2 times 0.041 divided by 12 squared. So that is 0.030 5 6 9, then 4. The 4 is recurring. So this is the same as 1 2 3 4 5 6. So that is the same as 0.00057. Okay, let me first write it as, because this is given in micro, so to bring a prefix we divide by its value. So I'm just going to divide by the value of 10 to the power of minus 6. So this is 0.0005694 divided by 10 to the power of minus 6. So that is 569.4 recurring, which is approximately 569, which is approximately 570 microfarads. Dividing by 10 to the power of minus 6, I'm changing to micro. Determine the resistance of R. So the incident V naught that is going to be our V naught, and this is going to be our V after time interval of from 0.01 to 0.02. That time is 0.01. So using the general equation, V equals to V naught e to the power of minus T over RC. So V after time t is 8, incident initial is 12, e to the power of minus 0.10 divided by the resistance R. The capacitance is 570, so it is 570 times 10 to the power of minus 6. So if we introduce ln, we have that ln of 8 divided by 12 is equal to the power of that, is equal to negative 0.10 divided by R times 570 times 10 to the power of minus 6. Trying to make R the subject, so I'll just say R equals to minus 0.10 divided by 570 times 10 to the power of minus 6 times ln of 8 over 12. So ln of 8 divided by 12, that is the answer, times 570 exponent minus 6. Then I'll say minus 0.1 divided by the answer, so it's 423. Let me try to check this again. I used the wrong value of t. T is 0.01. So this is 0.01. Sorry. So I have ln of 8 divided by 12 times 570 exponent minus 6. Then I have negative 0.01 divided by the answer, that is 43.2. So R is going to be 43.2. 43.2, so it's approximately 43. Define the magnetic flux density. Of course, we know that magnetic flux density from F equals to B as sine of theta. If theta is 90 degrees, then F equals to just B. So magnetic flux density is equal to F per unit current per unit length. So I'll say this is the force per unit current. Force per unit current acting on a unit length of wire carrying a current perpendicular to a uniform magnetic field. So the force acting on a long straight conductor carrying a current of 1 ampere per unit length, that is flux density, or the force per unit current acting on a unit length, that is the length of 1 meter, acting on a unit length of a wire carrying a current perpendicular to a uniform magnetic field. So I've defined that using this equation here, that B is force per unit current per unit length. But when I use force per unit current per unit length, I remember that the conductor must be at 90 degrees to the magnetic field. A long straight wire carries a current into the page. That's why we see a cross, as shown here in the figure. On the figure, draw 4 field lines to represent the magnetic field around the wire due to the current in it. So because the field is into the page, and this is our page, so using the right hand grip rule, which I demonstrated here, assuming that hold a conductor or hold your pen in your right hand with the thumb pointing onto the page or onto the paper on the table. And of course, we know that the magnetic field pattern around the wire are concentric circles. So they said 4 field lines. So I'll draw concentric circles around the wire. I always encourage my students to use a compass so that the, the concentric circles look very beautiful and uniform. Me, I'm using a free hand, but it's good when you use a compass to demonstrate this. So what is special about these field lines? One, they are concentric circles. That's number one. Number two, the separation between these lines increases as you move away from the wire because the field strength weakens as you move away from the wire. Please use a compass to draw something which is extremely neat. Use a compass. Use a compass in your set to draw something which is beautiful, with the center at where the cross is. That's where you put the sharp end of your compass, and you draw a very neat diagram for that. Okay. Then using the right hand grip, you notice that the fingers, of course, the thumb points in the direction of the current. So the thumb is pointing onto your paper, which you have placed on the table, and Folding your fingers, you notice that the fingers fold in a clockwise direction. So the magnetic field is in this direction, clockwise. Okay. Then two identical wires, X and Y, are placed parallel to each other. They are identical. The wires both carry current into the page, as shown in the figure. Explain why the two wires exert a magnetic force on each other. Of course, each of the wires must be sitting in the magnetic field of the other wire. For example, if I draw the magnetic field around wire X, it will extend into wire Y. If I draw the magnetic field around wire Y, it will extend into wire X. Of course, the direction of the magnetic fields are given by by the right-hand grip rule. And of course, both of them must be in this direction here. If we grip the conductor with the thumb pointing out to the page, in both cases, the magnetic field is in that direction. So each wire is sitting in the magnetic field of the other, and therefore by Fleming's left-hand rule, each wire is going to experience a force. For each wire is going to experience a force whose direction is given by Fleming's left-hand rule. Okay. So I will simply say each wire sits in the magnetic field created by the other wire. Or actually it is created by the current, so created by the current in the other wire. And the current in one wire is actually perpendicular to the magnetic field. Due to the other wire. For example, if we consider wire X, the magnetic field created by wire Y at wire X is a tangent in that direction. So this is the direction of the magnetic field. Yet the current is into the page. So it's like the magnetic field is perpendicular to the current. So the current in one, what did I say? The current in one wire is perpendicular to the magnetic field due to the other wire. And so by Fleming's left hand rule, a magnetic force acts the current in one wire is perpendicular to the magnetic field due to the other wire, and so by Fleming's left-hand rule, a magnetic force acts on the wire. Or acts on each wire. Let me just say acts on each wire. But it is simple. It is acts on each wire. On the figure, draw an arrow to show the direction of the magnetic force exerted on wire X. Label your arrow F. So I brought these ones here. I'll use the right-hand grip rule to show that the magnetic field of wire Y which is extending up to wire X. At the position of wire X, it is just upwards. It is just a tangent upwards. That's number one. And the current is into the page. That is represented by a cross. Now, using Fleming's left-hand rule, the first finger represents the field, the second finger represents the current, the thumb represents the force. So we must make the second finger to point onto the page, onto your question paper, which is on the table, and the first finger to point upwards, that is in the direction of B. So this is the magnetic field. This is the current, which is onto the page. And you notice that the thumb is pointing to, the thumb is going to point to the right-hand side. Therefore, they wanted an arrow here. So I'll draw an arrow here, which points towards the right-hand side. And this is F. They said label it F. So that is F. The current in X is doubled. The current is double the current in Y. State how the magnetic force exerted on wire Y compares with the magnetic force exerted on wire X. Of course, the magnetic force remains the same in magnitude. By Newton's third law, it is just equal but opposite. So I can say by Newton's third law, by Newton's third law, the forces have equal magnitude but act in opposite directions. Act in opposite directions. Or you would say the force depends on the product of the currents, which is the same for both wires. Therefore, the force is equal but opposite. The force depends on product of the two currents. And so equal in magnitude. So the force depends on the product of the two currents, and so equal in magnitude. I wrote each instead of equal. And so equal in magnitude. But the easiest is to look at Newton's third law. By Newton's third law, the force is going to be equal in magnitude but in opposite directions. The direction of the current in both wires is now reversed. State with the reason the effect of this change in the direction of the force on the wire. Now the direction of the force only depends on whether the currents are in the same direction or in opposite direction. If the direction of current in both wires is now reversed, it means, let's say it is now both out of the page. This is wire X, the other one is wire Y. Now out of the page in both cases. So it means the force again is going to remain in the same direction because both the currents in X and the field in both cases direction. In both cases they are reversed. So it means there is no change in the direction of the force, because if I try to draw the magnetic field pattern around the wire Y, which stretches up to wire X, and using the right hand grip rule, gripping my right hand, my pen in the right hand with the thumb pointing in the direction of the current above the page, so it means the magnetic field is in that direction. At this point is going to be a tangent downwards. But when I use Fleming's left hand rule, with the first finger pointing above the question paper, that is pointing towards the roof. Uh, I mean the first finger pointing downwards, not above, because the current is into the page, out of the page. The second finger is pointing towards the roof. Second finger pointing towards the roof to show that the current is out of the page with the question paper on the table. And when I make the first finger point downwards to show the direction of the magnetic field at point X caused by the wire, which is Y. First finger pointing downwards, second finger pointing towards the roof, the thumb again points in that direction. So the force is not valid because both currents have changed. But if one current had changed direction, then the force will change direction too. So I would simply say both the current, both the current, both the current in X and the field due to Y, because you see the field due to Y is now in the other way around, and the current has also changed direction. So both the current in X and the field due to Y have reversed. So there is no change in the direction of the force. So no change in the direction of the force. There's only change in direction if current in one of the wires changes or is in opposite direction to the current in the other. If the currents are in the same direction, the force is always attractive. The force from on X will be towards Y, and the force on Y will be towards X if the currents are in the same direction. If the currents are in the opposite directions, the force on X will be away from X, force on Y will also be away from Y. A polished sheet of magnesium in a vacuum emits electrons when it is illuminated by UV radiation. State the name of this phenomenon. It emits electrons, so that is going to be photoelectric effect. Photoelectric effect. For emission of electrons to occur, the frequency of the UV radiation must be at least 8.8 times 10 to the power of 14 Hertz. So this is the threshold frequency. Calculate the work function. So the work function energy is equal to H times F naught. So this is going to be equal to 6.63 times 10 to the power of minus 34, then times 8.8 times 10 to the power of 14. So that is 5.83 times 10 to the power of minus 19. So I'll just write 5.8 times 10 to the power of minus 19 joules. For ultraviolet radiation with the frequency 11 times 10 to the power of 14 Hertz, capture the maximum speed of the emitted electrons. So we know that the energy of the photons, which is HF, is equal to the work function energy plus the maximum kinetic energy plus Emax. So in other words, HF is equal to the work function plus a half m Vmax squared. So I'll make a substitution. H is 6.63 times 10 to the power of minus 34. The frequency is 11 times 10 to the power of 14. The work function is 5.8 times 10 to the power of minus 19 plus a half The mass is of the electron is 9.11. I don't know which mass is always quoted. I think it's 9.11, if not 9.1. So it's 9.11 times 10 to the power of minus 31. Then this is going to be times V max squared. So V max squared equals 2. So I'm just going to press my calculator once. So 6.63 exponent minus 34 times 11 exponent 14. Then minus the work function, which is 5.8 exponent minus 19. Then I'll multiply this by 2. Then I'll divide by the mass, which is 9.11 exponent minus 31. So that is 3.2777. 3.2. Then I find the square root. And that is 5.7 times 10 to the power of 5. So V max is 5.7 times 10 to the power of 5. Okay. The frequency F of the ultraviolet radiation incident on the magnesium sheet is varied between 8 times 10 to the power of 14, that's the work function, and 11 times 10 to the power of 14. On the figure, sketch the variation with F of the maximum kinetic energy Emax of the emitted electrons using the space below. Of course, we know that when the work function is, when H, we know that HF equals the work function plus Emax. If F equals to F naught, that is just threshold, it means H F naught is equal to the work function, and the maximum kinetic energy is going to be 0. So it means when the frequency is 8 times 10 to the power of 14, maximum kinetic energy is 0. So we have a point, because this is maximum kinetic energy against F, so we shall have a point which is 8.0. I mean 8.8. It was 8.8. The threshold was 8.8. So 8.8 times 10 to the power of 14 and then 0. It means anything below 8 is going to be 0 kinetic energy. So F less than 8.8 times 10 to the power of 14 implies that maximum kinetic energy is going to be 0. That is below the threshold. Then, of course, the maximum for F equals to 11 times 10 to the power of 14 hertz. Maximum kinetic energy is going to be a half times 9.11 times 10 to the power of minus 31, then times the maximum speed. Why should I waste time with this? Yet I can just subtract this one here. I'm just going to subtract. This is a wastage of time. So making Emax the subject, this is going to be, I'm using this equation here. So this is going to be HF minus the work function, which is the same as HF minus HF naught, which is H into F minus F naught. Therefore, it is going to be 6.63 times 10 to the power of minus 34 into 11 minus 8.8 times 10 to the power of 14, which is equal to, so 11 minus 8.8, answer times 1 exponent 14 times 6.63 exponent minus 34. So that is 1.458, approximately 1.46 times 10 to the power of minus 19 joules. You could get a 1.45 in case you used the maximum speed that we calculated. You might have got 1.45. If you used Emax equals to a half times 9.11 times 10 to the power of minus 31 times maybe 5.7 times 10 to the power of 5, but this is squared. You might have got a slightly different answer. Let's check. 0.5 times 9.11 exponent minus 31, then times 5.7 exponent 5, but this is squared. Actually, it is even higher, about 1.48 times 10 to the power of minus 19 joules. So whatever value you use. So I'm just going to now sketch the graph for 8.8. The scale here is 0.5 divided by 10, that is 0.05. So this is 8.6, 8.7, 8.8 is here. So along this is going to be 0. Use a ruler, very beautiful graph. Then I'm just going to look for 1.46, or you can plot 1.48. I'll look for 1.46. On the vertical, the scale is 0.052. So 1.45 is here. This is 1.45, so 1.46 must be slightly around there. So that is the point. So that is on the x-axis is 11.0 and 1.46. So I'm now just going to join the 2 points with a straight line because the graph always has the same shape. I'm going to slightly increase the thickness to make it bold and visible. Okay, so you can draw a better graph, better than that one. So I'll use extra more minutes because I give a lot of explanation. State the name of beta plus particle. Of course, beta plus particle is a positron, I think. Positive electron, that is a positron. Positron, this is R. Then show that the decay constant of fluorine 18 is 1.05 times 10 to the power of minus 4 seconds. So the decay constant is equal to ln of 2 divided by half-life, T a half. So this is going to be equal to ln of 2 divided by half-life, which is 110 minutes. So that is going to be 110 times 60. So ln of 2 divided by 110 times 60. So it's 1.050 times 10 to the power of minus 4. per second. Determine the activity of 2.1 times 10 to the power of minus 14 kilograms of fluorine 18. So we know that activity equals to lambda times n. And we also know that the number of moles is given by the number of molecules or number of particles divided by Avogadro's number, which is the same as the mass divided by the molar mass. Of course, this is the mass in grams divided by the molar mass in grams also. So it means the number of molecules is going to be equal to capital N is going to be mass over molar mass times Avogadro's number, which means this is going to be 2.1. I'm going to change it from kilograms to grams. So I'm going to say times 10 to the power of minus 12 times 10 to the power of 3 to change it to grams. This is to change it to grams. Divide by the mass. The molar mass is 18 grams. Avogadro's number is 6.02 times 10 to the power of 23. So I will just check this with my calculator. 2.1 exponent minus 12 times 1 exponent 3 times 6.02 exponent 23 divided by 18. So it's 7.02 times 10 to the power of 13. So the activity is going to be equal to 1.05 times 10 to the power of minus 4 times 7.02 times 10 to the power of 13. I'll just say times 7.4, times 1.05 1.05 exponent minus 4. So that is 3, how many? 1, 2, 3. That is 7.37 times 10 to the power of 9. Or I can write 7.4 times 10 to the power of 9 becquerels. A small sample of fluorine 18 injected into the body acts as a tracer for use in medical imaging. Describe how the interaction of beta plus particle with an electron in the body enables the formation of an image. Of course, your teacher must have told that the beta plus particle annihilates the electron, and their mass is converted into two gamma ray photons, which move in opposite directions and leave the body to the detector, which is around the body. So I will simply say the beta plus particle and the electron annihilate. What is the spelling of annihilate? Annihilate. Annihilate. That's number one. The mass of beta plus annihilate and their masses are converted into energy of 2 gamma photons. So the beta plus particle and electron annihilate and their masses are converted into the energy of 2 gamma photons. What happens to the 2 gamma photons? The 2 gamma photons travel in opposite directions. The 2 gamma photons travel in opposite directions and leave the body. To the detector. Remember, during the PET scan, the body or the patient is surrounded by a detector of gamma ray photons. So the gamma ray photons must leave the body and move outside to the detector surrounding the body, or to the detector surrounding the body. Then the arrival times are processed. So the difference in arrival times of the gamma photons is processed. The difference between the arrival times, I think when I write here, it will not be seen. The difference between the arrival times of the gamma photons is processed to generate an image of the tracer concentration. So the image just shows a point where the tracer is concentrating much in the body. So it's just an image of the tracer concentration in the body. Suggest why 10 minutes is a suitable half-life for nuclide used for a tracer. Well, it's not too short, so it can allow the diagnosis to take place, but it's also not too high, so it can easily be used up, or can easily get it can easily get it can easily be removed from the it can easily which word should I use? It can easily it doesn't take long in the body, because 110 minutes is not really a very long time. So they said suggest why 110 minutes is a suitable half-life for a nuclide used as a tracer in medical diagnosis. So we can say with a shorter half-life, a sample would almost fully decay before the test is done. If the half-life was say 2 minutes, so I would say with a shorter half-life, the sample would almost fully decay before the scan or before the test is complete, before the scan is complete or before the test is complete. Then if again it's longer, a longer half-life also would be a problem. So I would say a longer half-life again, it is going to expose the patient to harmful radiations for a long period of time. A longer half-life exposes the patient to harmful, or you can call them ionizing radiation unnecessarily. So if the half-life is again longer, then the patient is going to be overexposed to these harmful radiations, which is not necessary. Or I would say, if the half-life is longer, then it means you would need a larger dose of tracer to produce activity which is detectable, or with a longer half-life, a larger dose of the tracer is needed to produce a detectable activity. Remember that activity is equal to lambda times n, which is equal to ln of 2 divided by t a half times n. So if the half-life is longer, it means the activity is going to be smaller. So it means with a longer half-life, it means you will need a large dose to produce a detectable half-life. To produce a detectable activity, because if the half-life is bigger, then the activity is smaller. Okay, last question. I think I've used a lot of time. Explain how redshift leads to the idea that the universe is expanding. This is almost the same question every day. So one, redshift shows that redshift is actually the increase in the observed wavelength, and this means the radiation from distant galaxies has been observed to be redshifted. And the redshift is going to provide evidence that the galaxies from which the radiations whose wavelength is observed to increase are detected. The galaxies must be moving away, or they must be moving apart. And if galaxies are moving apart, then it means that the universe must be expanding, or must have started from the same point and is expanding. So I would say that redshift is the increase in the observed wavelength of light. Then radiations, no, we may not say light because I want to refer to radiations. So I'll just simply say radiations from distant galaxies let me use singular, radiation from distant galaxies is observed to be redshifted. This redshift provides evidence that the galaxies are moving apart, provides evidence that the galaxies are moving apart. If galaxies are moving apart, then the universe is expanding. If galaxies are moving apart, then it means that the universe must be expanding. And by the way, this also leads to the Big Bang. If the universe is expanding, then it must have started expanding from the same point in the distant past. And this is the idea of the Big Bang. Stars in a distant galaxy emit radiation. The total luminosity of the stars in the galaxies are 1.9 times 10 to the power of 36 watts. The emission spectrum of the radiation contains a line X at wavelength 658 nanometers. Radiation from the galaxies observed on the Earth. The observed radiation has a radiant flux intensity. Remember, radiant flux intensity is equal to L over 4 pi d squared. In the observed emission spectrum, line X is at a wavelength of 726 nanometers. Determine the distance d of the galaxy from the Earth. So, we know that the radiant flux intensity is the luminosity divided by 4 pi d squared. So it means d is going to be the square root of L over 4 pi f. So d is equal to the square root of 1.90 times 10 to the power of 36 divided by 4 pi times f, which f is this one here, that is 8.42 times 10 to the power of minus 16. So I'll press my calculator. So 1.9 exponent 36 divided by 4 pi times 8.42 exponent minus 16. Then I find the square root. So it's 1.34 times 10 to the power of 25. Then the speed v of the galaxy relative to the Earth. So we know that the apparent change in wavelength is equal to the ratio of the speeds v over c. So I'll just substitute the apparent change in wavelength. The observed wavelength, which is 726, minus the wavelength in the laboratory, which is 658, divided by the wavelength in the laboratory, which is 658. So this is the change in wavelength over the wavelength in the laboratory, should be equal to V divided by 3 times 10 to the power of 8. I'll just press my calculator. So we have 7 you notice that I've not added the units of nanometers because they cancel out. This is nanometers, this is nanometers. So their nanometer cancels out. So 726 minus 658 divided by 658, then times 3 exponent 8. So that is 3.1 times 10 to the power of 7. So V is 3.1 times 10 to the power of 7. Lastly, observations of many galaxies such as the one in B lead to many pairs of values of D and V. Plotting these values reveals a trend. On the figure, sketch the variation of V with a D. So we know that according to Hubble's constant, Hubble's law, V is directly proportional to D, or V is equal to H naught times D, which means this is just a straight line through the origin, according to Hubble's law. So I'm just going to sketch a straight line through the origin, use a ruler and draw a straight line through the origin. Okay. State the name of the quantity represented by the gradient. So if I have V equals to H naught times D, compare with the Y equals to mx plus c. There is no y-intercept. On the y-axis I have the speed, on the x-axis I have the distance, so the gradient is H naught. Gradient equals to H naught, which is Hubble's constant. So I'll just write here Hubble constant. I think that is the end of this paper. See you in paper 4.2. There will be no 4.1 because 4.3 because 4.1 and 4.3 are the same. So see you in paper 4.2. Until next time, bye bye.